Last two classes, we have been looking at scale invariant feature transform. In particular, we looked at two aspects. One of the aspect being finding out the dominant orientation and aligning each the patch around a given key point in that direction so that your repeatability will be invariant to rotation, right? That's one thing we discussed. Then another thing that we discussed, particularly in the last class, is about scale invariant feature transform detector, sorry, descriptor part. Like given a key point, how do you describe that? These are the two aspects that we have discussed so far, right? So maybe if you want me to mention here, this is a nice block diagram. We went in a slightly unconventional way. The reason being we have already seen a detector. It is not very different from it. So I wanted you to draw your utmost attention to the new things. So this is something we did. We started with aligning key point orientations and then building key point descriptors. Of course, go and play with your features is anyway. We will come back. We will start playing with them after the coming from the coming class. Okay. This then in this whole thing would fall under basically the detector part, which we are going to see today. Okay. This is basically descriptor. This is assigning key points, each key point a orientation. The point we are going to look at is SIFT detector. The good thing is the majority of the concepts involved in SIFT detector, we have discussed them while discussing about the scale invariant Harris corner detector. Okay, so anyway, there are few more upgradations to that, which we would get more clarity as we move on. So essentially, like scale invariant Harris transform, you will look for a key point not just spatially but in the sigma space as well, in the dimension of for varying values of window size also you are going to take a look at. And one function that makes the whole key point computation independent of the size, the value that you get independent of size is, what is the shape? This is basically Laplacian of Gaussian, LOG, right? So we discussed from the correlation point of view last class, not last class, in the scale invariant Harris detector on why it is very efficient in finding out kind of blobs. So that's usually also referred to as blob detector, right? And we then also discussed in the same class on what is an efficient way of computing the Laplacian of Gaussians.
Difference of Gaussians.
That's right. You do a difference of Gaussians. That would give you, you take the image, you smooth it with one variance, you take, let's say, sigma. You do now again on the image, original image, you apply a variance of k sigma. You subtract them both. What you get is very close to Laplacian of Gaussian. So if you want me to jump a bit and show you that, maybe I'll show you. This is a slide I just repeated here in this presentation, where we have seen that Laplacian of Gaussian can be computationally is almost equivalent to, here Laplacian of Gaussian is shown in color blue and in red you are shown as difference of Gaussians. So they are quite close, and this operation is computationally for performing it, it's more efficient. Okay, that's what we would be doing it. Now um so one, how it is becoming scale invariant, I explained it in one way there. This I am now just adding few more illustrations to computing this. Like for example, this is again an image which is quite similar to the scale invariant Harris transform. Let's say you have a curve like this in one image, right? if you are taking, assume that instead of a circular window here, you assume a circular, instead of rectangular window, you assume a circular window here. So it is indeed at this scale, it becomes a corner. Otherwise, if you are looking something like this, a very small window, if you are taking, this is as good as this is as good as this, this is as good as this is as good as this is almost like traversing along an edge, right? So it's not a good key point as such, because there are multiple possibilities that it can get mapped to. Okay. And this also we discussed it in the name of aperture problem, correct? But now if you take a window that is shown of this size, then this point now would behave as a corner. Now there is another image which is a zoomed out version of this is so you have a much bigger view of this, like this is shown in a full view there. It's much extent of this, maybe the edge, whatever it is, the object, whatever you may call it, or edge of that object is visible. Now you could see that here if you take this size, that's good enough, right? And then how do we find out? This is again almost a repetition of what we discussed in the Harris corner detector. So you are increasing the region size of your kernel, if you can call it so. Then you are going to compute a function here. That time to begin with, we just treated it as some black box. Then we came to Laplacian of Gaussians, right? And then this function would reach an extrema value here. So that means that's very, in case of Harris, right? That function reaching maximum is almost like you are around a the complete edge of the object. So any small movement there could cause you a big shift there. So similar thing here, right? So then what would you say? The scale here, at this scale, first point is this is a good corner point. Second point is that this scale here corresponds to the scale there. Okay, that's what it is. So in this particular image, while you are saying which is a corner point, so along with the locations of x comma y, so this changing the window size is equivalent to in varying the sigma value, right? And then that particular sigma value taking Laplacian of Gaussian value. So you have three values now. One is x location, assuming it's a 2D image. It has three vector of three parameters, x, y, and sigma, right? So more realistic image here than the earlier one. So if you are so perhaps this is the scale at which this point would be a good key point. So this is a zoomed version where you just zoomed in this particular part here, roughly this part. Okay, and that is this version here. So obviously now if you are having a size of here, depending on the zoom to cover the same thing, you require a window of a much bigger size. So assume that here x representing both x and y, in fact here, and sigma. So on the other hand here, x comma y comma a new value of sigma. So that also xy coordinates also would change there. And of course later you find mapping, which we would come in the subsequent classes. Now the question is here, how do I find the corresponding patch sizes in both, right? So this is an illustration here. You start, this is how the process follows. You start with a minimal size here, for example this, the scale, so at that scale you compute Laplacian of Gaussian. Here also at this scale you are going to compute the Laplacian of Gaussian. Next you increase the size further, you could notice there. Now this one, at that point you compute the Laplacian of Gaussian value, that's here, the value is here. You hope you are noticing here the size of this window is gradually increasing. You further increase, and you repeat the whole process. And after that you will notice that there is a maximum, this function is reaching here, this function is reaching maximum here. So this is maybe around something like this. So let's say 3.89, or let's say around 4 you have it. Here around 10 you have it. Okay, here around 4 your function Laplacian of Gaussian is reaching the maximum value there. So this 4 here corresponds to 10. So roughly you could see around 2.5 times the zooming effect is there. And this would tell you what is the size here for this, right? And of course, accordingly your window size would get fixed here. Okay, so here you could notice at a much larger width of your window, the same thing whatever you have here gets covered here, isn't it? So that's how you find out the optimal scale for each image. Yeah, is
So
that?
just to
Yes.
doubt, what is SQL? What function is SQL?
I'm sorry, I could not hear you.
What function is SQL?
ah this is Laplacian of Gaussian.
Okay, sir.
That's what. So I would just talk in bit more detail now about Laplacian of Gaussian also. We discussed it to some extent in the previous class, but I would further give you more insights there about this Laplacian of Gaussian. Look at here. So assume that you have an object of for illustrative purpose, we are considering simple objects like this. Okay, object of this radius or this radius. You could also interpret it in a slightly different way, or multiple ways. One way is you have a single image where you have circular shape objects of different sizes. That is one way you could look at it for certain understanding certain things. Another way you could think of is you have two images. One is a zoomed out or zoomed in version, and so this object has either become the other one, or this has become this, or this has become this, or other combinations are possible. Now what would happen is, here on the scale, you are taking the Laplace, you are convolving with the Laplacian of Gaussian, or correlating. It would just change the sign there with Laplacians of Gaussians with, is it increasing variance or decreasing variance?
Increasing variance.
Right. You are increasing the variance, and then what you are doing, convolving with an image that has just this thing, assume that, or the patch you have taken as just this thing. Then what would happen? It is at this scale, if you are getting a peak here, it is for this image at a higher variance you get the peak here, and even at a higher variance you get this peak here. The reason we explained in terms of correlation, okay, template matching, if you recollect. So it's something like you are summing up all the values that are there here. In fact, here they are correlating. If you are using this mask, inverted Mexican mask, if you are using it, then it is convolution. Anyway, it doesn't really matter. It's just like extrema is how you could think of. Okay, coming back here. So as the object size is increasing at higher values of sigma, you would get that function to have a peak. Okay, and again, we are not going to repeat the concepts that we discussed about the desirable properties of how this function should behave. And in fact, Laplacian of Gaussian nicely satisfies to a large extent all those properties. And another example here, so you will have quite a lot of literature on LOG, Laplacian of Gaussian, using applied for various applications, and particularly for blob detection applications, where this is not a complete result that I'm showing here. I think I have a reference to you. You just Google Laplacian of Gaussian blob detection. You get a very nice papers on that. You could go through it, but it is, for the time being, it is sufficient to take a look into this in a very similar lines of varying sigma and looking where you got maximum. You could capture this is what you would essentially, you could capture, you could roughly fit circles here to this shape. Okay, because that, if you see the base, it is more like a that is what you are taking. It roughly could could capture edges, uh, all very similar to, or you are just keeping that variance that you are plotting it around something like that, and you would end up something like this. Okay, that's why this is referred to as blob detector, because once you are varying your sigma value there, you get maximum at a scale that is similar to the radius of the region that you have here for a given object which is roughly circular. Is that clear?
Sir, could you
Yes.
go to the previous slide?
Yeah.
Um, Actually, the previous one, sir, where you have
Yeah.
2 images uh, before this also.
Okay.
Yeah, here.
Hmm.
Sir, so here you have it's written f of I of x comma sigma.
Hmm.
So is the I here the Gaussian and f the Laplacian? Is it like that?
On x-axis here, you are varying the sigma value. Okay. And this f of I is simply computing this Laplacian of Gaussian for this patch. That's all the values which are there inside is referred by I1 to Im, if I'm not wrong.
So we're just increasing the size of the Laplacian of Gaussian
That's right.
and plotting the graph.
That's right. That's right. You are right.
Here in this two images, we have
Hmm.
that X points, right,
Hmm.
marked as X in yellow
Hmm.
color
Okay.
around inside that square.
Right.
How exactly are we mapping those 2 points over there? Because
Okay.
once we
Yeah.
are fixing those points, then we are trying to increase the scale and check the maximum for
Right.
Laplace of Gaussians.
Right. I got your question. See, basically, you could get here n number of points here, right? And n number of points here in the second image. So how do you know that these 2 points are matching is your question, correct? For every point xy that you are considering as a candidate for key point, you are going to vary the sigma value for it, and taking that particular value of sigma for which, let's say, the Laplacian of Gaussian has got maximum value. So each point right now is described with xy comma sigma. It is not just xy. You do it irrespective of they are matching or not. Here for you, just to give an illustration, that when it is zoomed out, if the points are matching, somehow you find out that these 2 points are matching. How you find out? We are going to do it very soon, in the coming classes, next class or class after that. So it's now no more a point xy, but every point you are going to find out xy sigma. It is the same as what we did in scale invariant Harris. The message here is you will still find that same point but at a different sigma value based on what you are zooming in and zooming out, and this is able to handle this problem of scale, varying scale, where you could still find out. For example, if you consider the original Harris detector, there is no way that these 2 points can be found. Repeatability is no more there as far as the scale is concerned. But the moment you are varying sigma and plotting this whole function and then picking up these points, you are able to find out exactly the same point. And that comes at a cost. The cost being, now you are not just looking at xy, but also looking at xy and what is the window size that you use at which it is a good key point. If any of you have not, by the way, gone through the scale invariant Harris properly, please go back, because I now just mentioning those things which we discussed in detail in scale invariant Harris. So there we discussed, as you are increasing your variance value a lot, it would be equivalent to, in fact, applying a small value of variance on a resampled, or resampling here is in fact downsampling. So that on a downsampled image, this we discussed at good length there. We do it for the sake of computational efficiency, because if the moment your variance, your Gaussian kernel size increases, the number of computations you have to do would increase. So in order to do that, resampling is a simple thing. Downsampling is a simple operation. For example, you take every alternative row and column. That's a simple downsampling. Anyway, I'm going to discuss that in more detail. And one important computational trick that have been used in order to reduce the computational burden is, instead of computing the Laplacian of Gaussian on one side, you need to convolve with a Gaussian. Then you need to take Laplacian of it. Taking Laplacian of it would be equivalent to finding out dou square f by dou x square plus dou square f by dou y square and summing up. Of course, you would be using a window there for that purpose. But how people does for computational reasons is you just simply have difference of Gaussians. So how they are equal? This is a slide, repeated slide here. Both are equal. But if you want a more comprehensive reasoning on why they are more or less similar, this comes from heat equation. Hope you still remember something from your thermodynamics or from your +2, and I hope you could still recollect this equation from there. Dou G by dou sigma is equal to sigma times del square G. This is the heat equation that you would have studied in thermodynamics. Okay, so anyway, we are not interested in how we arrived at this equation. That I leave it to you. If you are interested, you could go further there. But the important thing I want you to take a look at is dou G by dou sigma is on one side. So what is a finite difference based approximation of it? If you look at it, see this G, you are taking a derivative of it with respect to sigma. So how do you do that now? I could write it as, so it's a function of x, y and sigma. So I could write it as you bring a variation in sigma by a value of k sigma you use, for example here. Then dou G by dou sigma, I could simply write it as sigma g of xy sigma minus g of xy k times sigma divided by, so dou G, difference in Gaussians for with these sigma and k sigma is this, and then take difference of these variances that you have taken. Okay, by this time, since you have already covered a finite difference based approach for Privet, Sobel, all those equations, forward difference scheme, you have seen it. You should be very comfortable by this time. I'm sure every one of you is fine with this part, right? Just the interchange of terms here, k sigma, sigma, compute the Gaussian, subtract k sigma minus sigma. This is an approximation to this, right? Because, and then sigma into, this is Laplacian of that Gaussian, right? Now how can you write that? So this I could write it as sigma into k minus 1 here, and then difference of Gaussians here is equivalent to, you take this denominator here, then it would be equivalent to sigma square into k minus 1 into del square G. Okay, now you consider some values here for the values of sigma and k. Okay, for example, sigma equal to 1.6, right? So this, and these are the typical values that the people would take. But the main point here I want you to observe, you could always manipulate both k and sigma are in your hands. Then you could see here the difference of Gaussians here is in fact proportional to the Laplacian of Gaussian. This is mathematically, if you want to see in a more formal way, this is how you could make an interpretation on why and how we could approximate Laplacians of Gaussian by difference of Gaussians. This was what we did. We have not gone through any math of it. We have just simply plotted them and see that numerically we have seen that both are very similar. And we, I hope you tried with your by hand drawing, where you change the sigma values and see you get something like a inverted Mexican hat. This is of a more formal approach, where you start with heat equation and see why difference of Gaussian is related to Laplacian of Gaussian. So we are more coming now more into how it has been implemented here. Yeah, again, that's a good point. If somebody could refer to what exactly is heat equation there and why exactly this Gaussian has to do, if somebody can tell it in more clear words, that would be great. I would request one of you, you students, to figure it out and let me know about that. I myself have not referred to the heat equation. I just assumed that it's a Gaussian. But it would be great if somebody refers, some of you refer it and let me know about that. Okay. You are going to compute Laplacian of Gaussians at different scales. That is equivalent to finding difference of Gaussians. Okay, hope everybody is clear with this. Now, in addition, I also told you that instead of applying a very large variance, at some point of time it's better you downsample your image and apply a small variance. That's also would be equivalent one. Okay, they will not be answer wise or the result wise, there will be no difference between them. So here what is done here is you keep increasing your sigma value here. Let's say here you have sigma k times sigma, k square times sigma, k cube times sigma, k power 4 times sigma. That you do here, and take difference between these two images. That's Laplacian of Gaussian for one scale. Similarly, take difference between these two, that would give you another one. Difference between these two would give you this. Difference between these two would give you this. Similarly, now you would take difference between these two, that would give you this difference between them, and so on. And of course, he has done a very extensive evaluation where how many times you resample. So he had done, I think if I'm not wrong, 8 times or something like that in his experiments he has done it. So perhaps that is the reason why he might be calling it as an octave, although at the end he figured out that resampling it for the take for a particular values of k and sigma that he has fixed out 3 is good enough, but still he is calling it as an octave, first octave and second octave, although at the end he is using only, David Lowe is using just 3 scales, but that's okay. So don't pay too much attention into octave should have, for example, 7 or 8 levels. I think 8, but it is having only 3 levels at the end. So don't get concerned about that. That's probably while he's doing experiments, he just for the sake of calling it, he is calling it as an octave there. Okay. And he did again a lot of experiments on what should be your starting point of sigma, and what should be the value of k, how many levels of k in each octave. I'll use for the sake of just consistency with the paper, I'll also call it as an octave. In each octave, how many levels should I take? A very extensive experimentation and a very large set of data has been done there. And he finally used k equal to root 2 and sigma k equal to root 2 and sigma of 0.707. That's what he has arrived at there. So another thing here is yeah, for these values of k, for example, just one point which it took a quite some time for me to figure out why he started with k square sigma here, which was not very obvious to me in the beginning. So let me just give you some idea about that. If you get it, good. If you don't get it, just leave it. It's just an implementation detail if you have want to implement this. So for example, he started with sigma here. At this level, he is considering root 2 times of sigma, so 1.414 times of sigma value here. At this level, he is applying a value of 2 sigma, here 2 root sigma, here 4 sigma. That's what he is applying. Now he is resampling this image, resampling it by a factor of 2, by a factor of 2 in row, by a factor of 2 in the column. So what would happen, for example, there is sigma in both x and y, by the way. So if you are doing it, let's say k square here, for this k equal to root 2, k square is 2 times. Since you have downsampled, now you just consider one row here. In one row, if you are taking only alternative pixels in that row, and then if you are still applying the same sigma value, since your image is now like coming half of that size, so this would be in fact equivalent to 2 sigma here, right? Sigma dash, if I call it here, or this is equivalent to applying 2 sigma in this image scale. So this is in fact equivalent to 4 sigma. So that way these two images are equivalent here. Hope you are getting that point. And then if you see there, then he is continuing here. So this is, so then after that, next is k cube sigma. So on top of it, he uses again multiply it with root 2, then multiply with 2, 2 root 2 and 4. Okay, so then this is then equivalent to taking between k power 4 sigma and k power 5 sigma. Okay, that's how you are doing it at different, that is how he is manipulating things when he is moving from one octave to other octave. If you get it, good. If you don't get it, don't worry, Just you
So, does resampling in this case means that we are scale, like we are taking only selective pixels of the image, like we
right.
are
You take
reducing number of pixels by
right.
net value of 4.
Exactly right. So if you have an n square size of an image of n by n, which equal into n square pixels, now your image size will become n by 2 by n by 2, because you will take alternative rows and alternative columns. So your image size would come down by a factor of 4. If you are looking at sigma value is same assuming in both x and y, because this is a 2D one. So this is equivalent to applying 2 sigma. So essentially this is equivalent to your in effect, this is equivalent to next take k power 5 sigma, k power 6 sigma and so on, and take difference. That is essentially in effect it is equivalent. But as I said, for computationally efficient way, you are simply downsampling. And suppose if you are getting here a particular point, you could always match to the octave which is below this by simply you know what you have removed, so you know where it goes in the given image. That's all. See, I want to vary sigma over a large range. Okay. Suppose at this point, I want to apply k power 5 times sigma, which is if you want this root 2 whole power 5, how much is that? So maybe if I'm not wrong, 4 root 2 times of sigma I want to apply. That Gaussian kernel is becoming too big, where you need to take the whole images, and at the end of the day, it is doing a simple averaging. Is it not? It would be in effect equivalent to actually downsampling your image and applying a kernel, Gaussian kernel, with a small value of sigma. Now you see here the sigma value has come here. Suppose k square sigma is equivalent to using a kernel of k power 4 sigma here on the original image. Okay. So then these are the scales. This calculation you could easily figure out based on what I told you now. So for example, if you want, these are the k values. No, not k value. What is that? 0.7. Yeah, sigma values that you are applying. Initially 0.707. Okay, which is roughly, if I am not wrong, this would be rough closely equal into 1 by root 2. Okay. Next time it is k sigma. K is root 2 into root 2. That's why this is 1. Then then 2 root. Then you have what is next? K square sigma. So into root 2. So which is 1.414. Okay, into root 2, that is 2, into root 2, 2.82. And next scale you started here with the k square sigma. K square is 2. 2 times sigma is 1 by root 2. So this is equivalent to 1.414. Okay, multiplied with root 2, 2, multiplied with root 2, 2.8, and so on. Okay, next one would start from here again. That's all. Okay, this is just he is giving you what all sigma values you have at a given scale, and then octave wise he is giving this. Here he is using different octaves. Here for each octave the scales are mentioned here. The the resulting sigma value. Here the sigma is sigma, here the sigma is k sigma, here it is k square sigma. The standard deviation is k square sigma. Just that is this table. Nothing to worry more about that. As I mentioned, to arrive at these optimal values for these what should be the k value and sigma values, he has considered 32 real images drawn from a diverse range, including outdoor scenes, human faces, aerial photographs, industrial photographs, and so on. And then each image was subjected to a range of transformations that include rotations, scaling, affine, change of brightness, okay, contrast changes, addition of image noise, and everything. Now since he knows the original image, and even after these changes he knows which are the corresponding points, so based on that he now computed the repeatability, and he changed the scales of sample per octave. So what if I use 2 levels, 3 levels, and 8 levels? As I mentioned, he found that 3 levels are reasonably good. Okay. And then he was looking at in terms of like repeatability in terms of matching location and scale, whether the scale is getting mapped rightly or not. And then nearest descriptor, there are other things, but whatever, we need not have to go into the details. What he found is 3 levels were good enough from his experiment, from his extensive experimentation. Okay. So then again he does similar things to figure out the value of sigma and find out 1.6 is good. finding out a key point is not just in xy. You do it now similar to the scale invariant Harris transform across the scales. So for a given point here, what would you do then? You look at a scale above it, a scale below it. Okay, so compare pixel with 26 pixels in current and adjacent scales. Select a pixel X if it is larger or smaller than all 26 pixels. Large number of extrema, computationally expensive. So detect the most stable subset with a coarse sampling scales. So essentially what it is telling you is, for any given pixel at a given scale, whether it is a key point or not, essentially you look at the adjacent scales. Both you would be looking both in the sigma space and as well as in the spatial one. Okay, and then if it is an extrema point, then only you consider that. Otherwise you do the same thing for another image, right? This is exactly what we discussed in Harris. Okay, but again on top of it there were scale invariant Harris, but on top of it, it does two more tricks, right? That's what I would like to mention here. First thing is, notice here you're taking one level sigma, next level is k sigma, okay, next level is k square sigma, and so on. Now maybe the maximum could be somewhere, if I had taken for example k by 2 sigma, that might be the scale at which it might be having maximum value, right? So is there any way I could figure it out? Can you tell me some solution on? So essentially when I assume that I'm doing it to sigma, k sigma, or this again, although I'm using sigma here, this is equally true for xy also. In other words, I talked in terms of sigma, but let me now talk the same thing in terms of the spatial one. Say for example, look at the pixels here. At one pixel I got this, at another pixel I got this, at another pixel I got this. Okay, now at another pixel I got this. Now it looks like this and this are extremas, but at a subpixel level the extrema might be here if I'm looking in the continuous domain. Is there any way that I could rather arrive at this rather than these points? Is there any way I could figure out these extremas mathematically? Something you used earlier in the Harris corner detector itself, there is something you have used which you could again use it here. Taylor series expansion. Okay, you take the Taylor series expansion. In now your space is x, y, sigma. Okay, this has to be very clear to you. So spatially, x might be moving delta x, y might be moving delta y, and the sigma value between your sampling is at sigma, k square sigma, and so on. It can be in between, let's say sigma and k sigma. So given a point, its value at the vector x, pay attention here, this vector x has location, okay, if you call it x, okay, location x, spatial locations x, y, and sigma. So you write 3D Taylor series expansion, and you know its value, the sample point is x here. Okay, that's where you know it for sure. After that, what you do, in order to find out where this function is achieving maximum, you simply take the first order extrema. In other words, it could be minimum also. So you differentiate it and make the derivative to be 0. So you need to take the derivative with respect to this x bar, okay, and make it to 0. that would give you the value there. Say for example, hope you all remember we already did this Taylor series expansion earlier. So f of x, if you are doing it, okay, so assume that you are doing it at x plus x bar. If you want me to write, to avoid confusion with this x delta x bar, you could write it as f of x bar plus, what would you do, dou f by dou x bar into this delta x bar, right? That is the kind of approach you do there. Similarly, this is what you are going to compute at, let's say, this point, right? And after that, the derivative of this function with respect to this x bar multiplied with this x, okay, that x is in fact whatever has been written there is in fact delta x bar, okay, that's what you have there. And then this x transpose x. So the best one is, I would strongly encourage all of you to go through this paper of David Lowe, which is extremely well written, okay. So please go there. I will make use of this again to yeah, for example, all of them which I covered here are originating of course from this paper itself. So I hope I could quickly look at those equations here. Better to explain from here, right? See here. uh, so that's what the Taylor series expansion you would be doing. And now you would equate it to, you take the derivative of it with respect to x bar. This is a constant anyway, because let me use a pen here. This is a constant here because that's value you are computing already. There's nothing to do with the derivative with respect to the x bar, new x bar location. Okay, here x, capital X bar is nothing but x plus delta x, you could consider there. And anyway, this dou d by dou x, you would have a value there. And this is then x square by 2 factorial, right? This you need to write it as transpose here. So this to have a similar effect, what you do there is x transpose x, x square. So you should be comfortable with writing Taylor series expansion for a vector where you would use matrices. And then when you make it to 0 and try to find out x, okay, I would leave this derivation part to you, but I would just show you something here. So these two would so this would be equal to 0 when you take the derivative. So see how you take this derivative here, and essentially then notice that this is a constant value. Similarly, dou square d by dou x square is also a constant value. So when you try to find it out, this inverse would come there multiplied with dou d by dou x. That's what would come here. X square is there in a way. So I'm just giving an intuitive reasoning on why you arrive that, but I leave it to work out clearly for yourself. So something like x square, you take derivative, so it becomes 2x, x and x gets cancelled. This x is essentially take derivative with respect to x would be equivalent to 1. So it should make sense the moment you, I think the easiest way to do look at it is look at it as if it is a scalar, and then that's how I'm giving you the interpretation. I leave it to you for extending it to a vector when x is a vector. So hope this is clear to you. So coming back here now, you could now find out actually the location where this function, what is the maximum location in within this. You have samples, but now you could figure out, thanks to the Taylor series expansion, using that while you are doing curve fitting, you could find out the exact region where it is reaching maximum value, right? And then just to avoid very, so these basically these values of the extremas will be normalized to 0 to 1, and you put a threshold there and drop all those points. So in the first difference of Gaussians, when you are doing, you will pick up some key points there. On it, you will further fine tune and find them at a subpixel accuracies, and also in terms of the scaling, in terms of sigma, you would find out them. So you have a more localized key points there, accurately localized key points, and on that you are going to apply a threshold, and anything below that threshold you are going to drop them. For example, applying difference of Gaussians on the original image has given him 832 key points. Here each key point is shown by its magnitude. What you got is shown by the length of this arrow, and orientation by this direction of your this arrow. These are the two things they used. And out of that, now after localizing them using this Taylor series expansion and applying a threshold of 0.03 from 832, this has come down to 729. Those are the number of key points that you got there. So for example, let me show the same result here. So by the way, the original image is of size 239 by 189, and then he just using difference of Gaussians and both scales and space, you compare with the 9 above, 9 below, 8 surrounding it, keeping it only if it is maximum, has given him 832, and applying that 0.03 or whatever has given him after thresholding, it has given you 729. But still there is a problem here that has not yet been addressed. What is the problem with these key points? Just you mention the problem and then I leave you. There is something that where this key points could give you a wrong key, that's not really a key point. Where is the problem? That has not been addressed so far. So I will write the kernel, and then probably you could write it. Suppose I have something like this. Okay, this is my Laplacian. Now you tell me what is the problem that is still persisting in these 729 key points. Have any idea about that? You think about it. You tell me the problem in the next class, and then we will see a solution for that also. Okay, then I'll stop here. Right. Thanks. You could continue if you have a next class. Yeah, stop here. Bye. Take care.